In this video, we're going to be discussing section 1.5, which covers hybridization and hybrid orbitals. So as we saw in the last video, when we look at the structure of methane, CH4, we see that there is our central carbon attached to 4 different hydrogens. And we said that the angles in which a hydrogen through the carbon and to another hydrogen makes is around 109.5. We said that this geometry is referred to as the tetrahedral geometry. And so in this section, we're going to discuss a little bit more about the actual bonding that occurs between this carbon and the respective hydrogens, and specifically talk about the types of orbitals that are involved in those bonds. So if we look at the electron configuration of carbon, it doesn't seem to fit well with what we expect for the bonding of carbon to the 4 hydrogens found in methane. As you can see from the lowest energy electron configuration, we have 2 electrons in the 1s, 2 electrons in the 2s, and then we have 2 p orbitals at the 2p level that contain a single electron. If we were to look at this electron configuration and try to understand the bonding that carbon will make with neighboring elements, we might suspect that it's only going to form 2 bonds to its nearest neighbors. Because as shown, the 2s level is completely full and so unable to accept an electron through the formation of a covalent bond with a neighboring element. And so this idea of the lowest electron configuration doesn't really satisfy what we would expect for the bonding to carbon. Now, if we were to take this same configuration, but now have one of the electrons in the 2s promoting it to that empty 2p orbital, now you can see that we have 4 half-filled orbitals. We have a 2s and 3 2p orbitals that all only have a single electron. As a result, what we'd expect is that these orbitals, as pure p's and the s, could potentially form individual bonds with neighboring elements. But as I mentioned previously in the previous video about our bonding theory that we typically use, the valence bond theory, we said that orbital overlap is very important. But also recall that the shapes of the s orbitals and the p orbitals, they're quite different. And so you'd expect that one of the bonds in methane would be stronger than the other 3 bonds based on the relative shapes of these orbitals, because the s orbital generally has better overlap with neighboring orbitals than the p orbitals. So even this excitation version of the electron configuration doesn't completely explain what we observe experimentally in terms of the bond lengths. Each of the bond lengths in methane, the CH bonds, are identical. And so, although this aspect of excitation promoting one electron from the 2s to the 2p is accurate, it is what happens after this that is quite relevant. So in actuality, when atomic centers bond with neighboring elements, other atoms, what we observe experimentally is a mixing of these orbitals to form hybrid orbitals. And so this process of taking a pure 2s and 3 pure 2p orbitals and combining them, the net result of this combination, of this hybridization, so to speak, is the formation of 4 new orbitals. And we give names to these orbitals based on the pure p orbitals and s orbitals from which they come. And so given that we have a 2s mixing with 3 2p's, the net result is 4 sp3 hybridized orbitals. So orbital hybridization is, in a sense, a mathematical way of describing the mixing of pure atomic orbitals, And we're not going to be focusing on the mathematics behind it, but we will look at the relative shapes of the orbitals that result from this mixing. So when we mix, again, the pure P's with the S, we refer to this mixing as hybridization. And the net result is we form hybridized atomic orbitals. And so these hybridized atomic orbitals will have some character of the original orbitals. So that means that each of these orbitals resulting from hybridization, 1/4 of them will be what was from the 2s, and the remaining 3/4 will be what's resulting from the 2p's from which they came. Also, a good way of remembering this is that 4 orbitals went into the mix, an s and 3 p's. So mixing 4 orbitals together, you will get 4 hybridized orbitals coming out after hybridization. And so this hybridization idea really is important because it shows us now that we do have 4 orbitals, hybridized orbitals, that are importantly equivalent in energy. These are degenerate. They have equal energy on our y-axis. And so this now is a better description of what we observe when carbon forms covalent bonds with neighboring atoms, as in methane with hydrogens. And so it's going to be the overlap of an sp3 hybridized orbital on carbon with the 1s orbital of hydrogen that forms that covalent bond. So let's look at that image in a little bit more detail. So here's the structure of methane, CH4, but now what we're including into our diagram is these new sp3 hybridized orbitals. And so you can see that here we have our carbon center, and we have a sp3 hybridized orbital containing a single electron in this location, and then we also have one here, a third here, and a fourth as shown. And so again, these 4 orbitals take up that tetrahedral geometry. They make up that tetrahedral geometry that we saw earlier in our example. So the angles are still, as we described earlier, 109.5 from this hydrogen to this hydrogen. So this is the unbound state, so showing carbon possessing the 4 sp3 hybrids. Here are the 1s orbitals of hydrogen. Hydrogen, again, only a single electron present, and so therefore we have a half-filled 1s orbital that can undergo bond formation through covalent interaction with these sp3 hybridized orbitals. So this is the net resultant. You see that we have methane, we have 4 sp3s sigma bonds. So again, we identify the nature of a sigma bond based on the orbitals that are overlapping with one another. So we have here the overlap of an sp3 hybrid on carbon with the 1s orbital of hydrogen. And so we show that overlap in this diagram, as you see here. And so the nature of the bonding for methane, now that equivalency between all the carbon-hydrogen bonds is accurately depicted with this hybridization idea. And so in methane, we have 4 degenerate sp3 hybrid orbitals, and they overlap with the s orbitals of hydrogen to give you your covalently bound structure. Now let's look at another example. Let's look at ethane. And you can see for ethane, the only real difference for ethane, and we can draw the structure of ethane. Ethane with a line bond structure is simply just a straight line, and the endpoints referring to carbons fully saturated with hydrogens, and we'll discuss that in a little bit more detail in section 2 on how we draw our organic structures. So that's one way ethane is shown, but you've also seen it in this manner, where we have two CH3s attached by a single bond between the two carbons. So if we look at the hybridized picture, again, we still have carbon in an sp3 hybridized state. So both of these carbons are sp3 hybridized, and as a result, we're going to have 4 sp3 hybrid orbitals for each carbon. The only difference between methane and ethane is that 3 of these sp3 hybrids are forming sigma bonds with the 1s orbitals of hydrogen, and the remaining sp3 hybrid on each of the carbons forms its own sigma bond through that sp3 orbital overlap. Now the angles will be slightly different for ethane than methane, and again that has to do with the differences in the size of the carbon atoms and so forth, but generally they're taking on this tetrahedral arrangement around those carbons, so fairly close to 109.5. Now what happens if we go beyond just our sigma bond containing compounds? So if we look at systems that contain bonding other than the single bond, and we think of examples where we have double and triple bonds, let's look at how we can explain hybridization for those particular systems. So the simplest example of a hydrocarbon, that is a carbon and hydrogen containing molecule that has bonds other than just single sigma bonds, is that of ethene. Ethene, as you can see here, or also commonly known as ethylene. Ethene is a 2-carbon hydrocarbon, and you can see that there is a double bond between the 2 carbons in ethene. As a result of this double bond, what we typically observed is these structures have some planarity to them. So you may recall the trigonal planar system in the previous video, where the molecule was relatively flat. And that's the same as what we observe here, that ethene has the double bond, and as a result of that, it has planar geometry. Now, how do we describe the structure of ethene using the idea of hybridization and hybrid orbitals? Let's look at that in the next slide. So if we go back to our electron configuration for carbon, again, we're looking at what we call this excited form of carbon, where there is a promotion of a single electron from the 2s to one of the empty 2p's. And again, that gives rise to these 4 available half-filled orbitals, a pure s and 3 pure p's. Now, when we look at the hybridized picture for ethene, one distinct difference between that of methane and ethane is that not all of these half-filled orbitals are going to be mixed. As you can see by this image, what's shown in the dotted ellipse is that we're only going to mix 3 of those 4 half-filled orbitals. And so the net result of hybridizing these 3 is that we end up with 3 degenerate sp2 orbitals. So again, sp3 was the result of mixing an s and 3 p's. In this example, we're mixing an s with 2 p's. And so the term that we use to describe the resulting hybridized orbital is an sp2 hybridized orbital. This is important that only 3 of them are being mixed, because what that means is that this 3rd p orbital is no longer being mixed, no longer undergoing hybridization. So it's available for forming other types of bonds, specifically a pi bond, which is part of our double bond. So the hybridized picture for ethene is that upon hybridization, you form, or I should say, you have 1 p orbital that is left unchanged. So we have 1 p orbital available, and as a result of mixing the s and the 2 p's, we end up with 3 sp2 hybridized orbitals. And so this is what the structure, the hybridized structure of carbon looks like when you have an sp2 hybridized system. The result is that we have this single p orbital shown by the blue and red lobes. And then what's shown in gray are the sp2 hybrids. Those sp2 hybrids are going to lie in the same plane, whereas the p orbital will be orthogonal to that or make a 90-degree angle with each of those sp2 hybrids. And so that's what an sp2 hybridized orbital looks like for carbon. Now, if we look at one of the simplest structures, which we just introduced previously, of ethene, if we now look at that hybridized picture, this is what we see. We see that we have our two carbons. They're sp2 hybridized, which means there's 3 sp2 hybrids all in the same plane around each of those carbons. And orthogonal to that plane, perpendicular, are the p orbitals. One on this carbon and a second on the other. It's these two p orbitals that can form a pi bond. It's not being shown here in this diagram, but typically what we'll do is we'll draw a line between the lobes to represent that there's overlap or interaction between those two p orbitals. And that interaction between two p orbitals is referred to as a pi bond. And we usually give it the symbol pi. So a pi bond is the result of overlap between two p orbitals, and all the other bonds in this example are the result of overlapping sp2 hybridized orbitals with either another sp2 hybridized orbital, which is shown for this sigma bond between the two carbons, or we have an sp2 hybrid overlapping with the 1s orbital of the hydrogens attached. And so again, that gives us our structure for ethene. And all of these hydrogens and carbons are lying in the same plane. And the double bond is formed between two p orbitals that are orthogonal to that plane. So that's the valence bond picture of the bonding in ethene. And as I've just mentioned, the p orbitals overlap to form what we refer to as a pi bond. And overlap occurs both above and below the plane. So we see overlap in this region as well as in this region. Don't be too concerned about the relative colors of these lobes. That is something that we discuss in more detail when we look at molecular orbital theory, and that refers to the various phases of these lobes. But again, for the valence bond theory, we don't have to concern ourselves with those additional details. For the most part, the valence bond theory is quite good at helping us understand the bonding that we observe in most organic compounds. And so again, this bonding, this overlap results in a pi bond between these two p orbitals. Now, our last example that we want to look at when we talk about hybridization and hybrid orbitals is that of how do we describe a triply bound system, or a system that contains either two pi bonds, or in this case, a triple bond between two elements. And so the simplest example of an alkyne is ethyne, a two-carbon system shown here, where we have a triple bond between the two carbons in ethyne, also commonly known as acetylene. Ethyne has a triple bond, and as a result of that, has a linear geometry. So we've gone from tetrahedral with methane to planar geometry with ethene, and now in our ethyne example, we observe linear geometry. So we want to show you how, using this valence bond theory and this hybridization picture, how we can describe this linear geometry that we typically observe. So similar to how we approached methane and ethene, in ethine, when you look at the structure and you see that triple bond is composed of a single sigma bond, so a sigma bond, and 2 pi bonds. Now, in order to form 2 pi bonds with a carbon in ethine, we need to have 2 available p orbitals. And that's the easiest way, in my opinion, to distinguish the hybridization states of carbons, is to look at the types of bonds that are being formed to that particular atom, carbon atom, or any atom. You can use this method of hybridization for really any atomic center, but we're focusing on carbon just as an introductory examples. So if there are 2 pi bonds formed to each carbon in ethine, then that means that we need to leave 2 of the p orbitals unmixed, because pi bonds are only going to form between original unmixed p orbitals, or pure p orbitals, orbitals that are not affected by the hybridization process. So as a result, if we have to keep 2 of these 2p orbitals unmixed, then that would imply that what's remaining, what's left, is mixed. So the 2s orbital and one of the 2b's do mix, and those 2s and 2p, those 2 orbitals mixing, give rise to 2 degenerate sp orbitals. Again, we use the term sp to indicate that that hybrid orbital was produced from the hybridization of an s and a p, and only an s and a p. So 2 orbitals went into the mix, and so as a result, 2 equal energy orbitals, degenerate orbitals, come out of that hybridization process as 2 sp orbitals. So the sp orbitals will be involved in the formation of the sigma bond, whereas the 2 half-filled p orbitals on each carbon will be involved in the pi bonds between the 2 carbons in ethine. So let's look at that. So here's a single carbon and the structure of the single carbon using this hybridized picture. And so we have our central carbon atom, and the orbitals associated with an sp hybridized carbon center are as follows. We have a single p orbital shown by this red and blue double lobe p orbital. And then we have orthogonal to that, 90 degrees and somewhat coming out at you in the plane, is this p orbital. Okay, so we have 2 p orbitals around this carbon center. These are the unmixed p orbitals. And as a result, these are the orbitals that are involved in pi bonds. What's left is an sp orbital here and a second sp orbital here. And they are also 180 degrees away from one another. So this is slightly out of the plane, this is slightly behind the plane of the screen. So this is what an sp hybridized atomic center looks like. You have 2 p orbitals associated with it, as well as 2 sp orbitals, hybrid orbitals. So for ethine, how do we show that? We show it in this way, where each p orbital on each of the carbons, the p orbitals that are parallel to one another will form 1 pi bond, and the other 2 p orbitals that are parallel to each other will form the second p bond. So I can show that through connecting these 2 p orbitals with 2 lines to represent that those 2 p orbitals are overlapping to form 1 pi bond, and then I can use a different color here to show the overlap between the other p orbitals, 1 on each carbon, that overlap to form the second pi bond. So that's how the 2 pi bonds are formed in ethine, and you can see that the remaining sp-sp overlap between the 2 carbons gives us our sigma bond between the 2 carbons, and then the other sp hybrid orbital overlaps with the 1s of a hydrogen, in these two cases to give you the two sigma bonds to hydrogen that is observed for ethyne. So we have our sigma bond shown here for each of the carbon hydrogens, and then this triple bond is formed from a sigma and 2 pi bonds. So there's 3 bonds associated with the triple bond, and the sigma bond is as a result of this sp-sp hybrid orbital overlap, and the remaining pi bonds, as we discussed, is due to the overlap. In a sense, we refer to this as sort of a sideways overlap, but we have 2 parallel p orbitals that overlap in that sideways manner to form pi bonds. So this is how we describe valence bond theory when looking at hybridization in hybrid orbitals, determining the hybrid orbitals that are involved for a particular atomic center. It's always defined by the type of bonding to the neighboring elements. So if you see an atomic center that has only sigma bonds to it and possibly lone pairs, as we saw for ammonia or water, these are all sp3 hybridized systems. And that's because there's no pi bonding involved in that particular structure. Once you have a single pi bond associated with an atomic center, then you know that the hybridization of that particular center has changed from sp3 to sp2, and that gives rise to a different shape. So we go from the sp3 hybridized picture, which is more tetrahedral in nature, to a planar geometry with the sp2 system. And now we've seen in this example, and again, I'll just draw it up quickly, that in our ethyne example, this is the bond line structure for ethyne, we have this linear geometry. If I just show for visual aid the hydrogens, the angle between these two sp-s sigma bonds between the carbons in ethyne and their terminal hydrogens is 180 degrees. And so we have this linear geometry that we expect based on the hybridized picture. So you're seeing now that we've looked at hybridization in detail, and that can too explain in a lot of detail the nature of the shape and molecular geometry of small molecules. And we can use the VS-EPR model as well to help with, shape. So with both of those models in mind, we should be able to predict with fairly good accuracy what the shape of small molecules looks like, as well as how the shape and geometry of a larger molecule, how it changes in different regions of that molecule based on hybridization and based on the repulsion between bonding pairs of electrons and non-bonding pairs. So if you have any questions about hybridization and hybrid orbitals, by all means, send me an email or start a discussion in our class forum. Thank you.